Around the year 2000, my colleague Christine Barth, in her survey mission, discovered an unexpected series of photographs, and she immediately contacted me. When I saw these images, I knew what it was and what I was looking at. I think I just briefly said, those are color photographs by Becquerel. This short statement did not reflect my excitement to discover those images. And such a small rainbow frozen on a metal plate might be insignificant for most people, but it is a milestone in the technical history of photography. This is the earliest color photograph produced in 1848. The origin of colors remained a source of mystery and debate for over 100 years. And then, a couple of years ago, we decided to study those plates and this photographic process in details. But let me give you an explanation first about the context. We are here in 1839 in Paris at the Academy of Sciences, and its talented secretary, François Arago, has learned of Daguerre's invention, the daguerreotype. The unmistakable quality and precision of the image provided by this new photographic process excite Arago. Because with the daguerreotype, Arago has a tool that will not only serve to document the world, but will be useful for science and scientists. Of course, the scientists of the Academy of Sciences were in the front row to study this mind-blowing photographic process. However, those early images had no color. For Arago, this problem will be resolved on the day a substance that records the color of light will be discovered. This declaration led researchers to seek a chameleon substance capable of recording directly and representing all the color. Among them, a young scientist, Edmond Becquerel, is involved in this research. He's only 19 years old, but his father, César Becquerel, member of the Science Academy, had already recruited him as his personal assistant in his physics laboratory at the Museum of Natural History. Of course, even at this time, it was considered a bit odd that a father would recruit his son. César Becquerel's answers to this criticism was straightforward. He said, "I did not recruit my son. I recruited the best candidate, and it happened to be my son." This became almost a family tradition, as the Museum of Natural History welcomed 4 generations of Becquerels, one of whom, Henry, received the Nobel Prize for Physics. But let's go back to Edmond Becquerel. He is highly productive. In addition to discovering what would later be known as a photovoltaic effect, he quantitatively evaluated the impact of each color of light on a daguerreotype plate. Edmond Becquerel was among the first to assess quantitatively the impact of each color of light on the daguerreotype on the silver iodide. These researches led him in 1848 to introduce a color photographic process that was surprisingly simple. A silver plate is immersed in a solution of chlorides to produce a layer of silver chloride on the surface. And when exposed to red light, this silver chloride layer turns pink. When exposed to a blue light, it turns blue. Under a green light, it turns green, and so on. Becquerel exposed such a plate to the solar spectrum, and color could record directly without any processing. A colored image of the spectrum was formed. A kind of instant image, actually not that instant, because the exposure could last more than 1 hour. Those images can be kept for more than a century in the dark, but they fade in the light. And for me, after 170 years, it was unexpected to find those fragile images in relatively good condition. This discovery reactivates an old question about this amazing color photographic process. Where did the color come from? During the 19th century, some physicists suggested that the colors were due to a light interference phenomenon. For other scientists, the color might be due to the formation of pigments. Our doctoral students explored this question in details a few years ago. The difficulty in analyzing those plates using spectroscopic or imaging techniques is that the plates are still very sensitive to visible light, UV or X-ray, as well as to electron beams, which can lead to changes in the structure or composition of the color image during analysis. We can succeed in avoiding those interactions by working at low temperature with a limited dose of photon. The morphology of the image material was characterized by electron microscopy combined with electron and X-ray spectroscopy. We could not see any periodic structure of the material that would indicate an interferential phenomenon. Now we were able to identify different oxidation states that could explain the difference of colors. On the other hand, statistical study of the silver nanoparticles shapes present on the silver chloride deposit reveals that exposure to various colored lights causes a phenomenon of photoadaptation of those silver nanoparticles. We observed significant differences in the number of nanoparticles, their location, and their distributions of size and shapes depending on color. For example, a blue area has a large number of small nanoparticles, below 30 nanometers, embedded in the silver chloride grain. The size and distribution of these nanoparticles is the origin of color. This is known as a plasmonic effect.